Okay, chapter 1, section 7, problem number 2 was asked about. So let's take a look at this graph so we know what we're talking about here. So it says from 0 to 4, 1, 2, 3, 4, it's x squared minus 5. Well, x squared is a parabola, and minus 5 brings it down 5 units. 2, 3, 4, 5. So it'd be here, and if I move over 1, a normal parabola, there's no stretch on it, would go up 1. And if I move over 2, it goes up 4. And if I move over 3, it goes up 9. From 5 would be up to positive 4. Okay? And this is a solid dot here, and this one's open. And then at 5, oh, I had to go to 4. So if I go over 4, 4 squared is 16, minus 5 is 11. So 5, 6, 7, 8, 9, 10, 11. It's up here where it's open. So it goes through here and gets up to there. And so we're at 4, 11, but it doesn't exist there. Then it says at 4, be at 5. 1, 2, 3, 4, 5. So that means it's putting a dot there, and that's only that place. And after 4, when x is bigger than 4, or 4 is less than the x's, do this. Well, this is a line of slope 4 starting at negative 5, and the line of slope 4. So it would go up 4 for 1, up 4 for 1, and so on. So I'm going to figure out where we're at 4. So that's 4. 4 times 4 is 16, minus 5 is 11. And then I've got to go up 4 for every 1 on that. So it will go up like this, and it goes on forever. So that's what we're looking at. And it says, what's the limit of this function? What height does it approach as we get closer and closer to plus 4? From the positive side. So if I'm coming from the positive side, it's headed towards 11. If I approach 4 from the negative side, it's also going towards 11. And it says, what's the limit at 4? Well, then it's 11. And that's the answer. Didn't need to do all this other stuff. That was it. Now, is it continuous at 4? The answer to that is no, because the value doesn't equal the limit. It has a limit. As a left and right, they're the same, so it has a limit, but the limit is not equal to the value, so it's not continuous there. All right, next one, 5. So we've got this, and it says, draw this everywhere when x is not 2, and then k when it is 2. And make it so the function is continuous on any interval. So at 2, this has a hole because I can't put 2 in there. So let's see what the hole is. Now, the way you find holes is, hopefully this is a factor of this. So I'm going to try to factor that. So I got 3x to the 5th minus 6x to the 4th. There's a 3 in both of them, and there's an x to the 4th in both of them. And when I pull that out, 3x to the 4th times x would be 3x to the 5th. And 3x to the 4th times a negative 2 would be 6x to the 4th. and that's divided by x minus 2. These cancel. So 3x to the fourth is what this thing looks like, except it's not exactly this because this has a hole in it. So we need to pick a k to fill that hole in. So at 2, we can't put it in this, but we can put it in there. And 2 to the fourth is 16. 16 times 3 is 48. So if k was 48, it would fill in the hole in this graph. Now you can go ahead and graph this on Desmos, slide your cursor until you find, get to 2, and it'll look like it's about 48. And that's the number we need to put there to make the function continuous. All right, number 8. For each of the following prompts, give an example of a function that satisfies the criteria for a formula or a graph, which, with reasoning, is sufficient for each. If no such example is possible, explain why. We want a function that's continuous at 2. To be continuous, it has to have a left-hand limit, a right-hand limit, and they got to be equal, so it has a limit, has a value, and they're the same. So we have a continuous function at 2, but it's not differentiable. Now, to be differentiable, 2 things have to happen. It has to be continuous, and it has to have no cusp. Well, it is continuous, so the only way it would be non-differentiable is to have a cusp at 2. So I'll just draw a graph and put 1, 2, and I'll make a graph that has a sharp point at 2, so there's not a single tangent line to it. It could be anything that changes direction instantly at 2. So there's A. B, a function g that is differentiable at a3 but does not have a limit. Now, to be differentiable, it has to be continuous. To be continuous, it has to have a limit. So this is not possible. It can't be differentiable and not have a limit anywhere. Function h that has a limit at -2 is defined at -2 but is not continuous. Well, at -2, to have a limit, the graph has to approach a value from both sides, the same value. And it has to be defined. Well, if it was defined to be there, then it would be continuous. So must be that it's being defined, its value is not what the limit is. And that's an example of something that would be not continuous, but have a value, whatever the height this is, looks like maybe 1, and it has a limit. The limit might be 2. It looks like it's approaching 2, but the value is 1, and so it's not continuous. Okay, D, P that satisfies the following. It has a value, so I'll draw a picture of P. At -1, it's 3. The limit as we approach -1 is 2. So as it gets closer and closer to the -1, it's going towards 2, but then it has a value of 3. And then the value at 0 is 1. So somehow it has to get to 1. And the slope at 0 is 0. So it has to go flat right there. And so now I've got that. And then as we get closer to 1, the limit and the value are the same, but there's no derivative. It's not differentiable. So to be not differentiable, there needs to be a cusp. So whatever height it goes to at 1, it doesn't say what it has to be, the value and the limit are the same, and so that means it's got to go to that place from both sides. It's got to be at the same height, but it can't have a derivative, which means we got to put a cusp there. So it's getting closer to some value, and which is the limit. So the limit and the value are the same, but it's not differentiable. There's no derivative. So that would be an example of that one.